Next, let's talk about some of the applications of parametric equations. And first of all, I would like to answer the question, why do we need parametric equations? And is it possible for us to continue living our lives without considering the parametric equation? And the answer is no. We cannot live without or ignoring parametric equations, and here's one of the simple reasons why. All of you have seen a wheel, and all of you have seen a wheel in motion. So when the wheel rotates, it's a self-explanatory motion. And now let's imagine that as the wheel rotates, it rolled over a piece of bubble gum, and if you now keep track of the if you lock your eyes on the bubble gum, what would be the trajectory of this bubble gum? And turns out, so again, if the wheel rolls on this surface and this is the bubble gum, so what's the trajectory? Some people mistakenly assume that the bubble gum will move backwards briefly, creating some sort of loop like this, which is actually not true. The bubble gum will continue moving forward at all times, so its motion will be somewhat like this. And if you look at it, this trajectory clearly passes the vertical line test. So the graph of this trajectory is a function. So this is a function, clearly. It's a function because it passes the vertical line test. So the question is, if it's a function, can we write it as y equal f of x? Can we use some sort of laws of motion to figure out the function that represents this trajectory? And the answer is no. It is actually impossible. So it is impossible to express this trajectory in terms of explicit function y equals f of x. But it is a function. So we can try to do it implicitly, and it's not going to be pretty at all. However, we can use some simple geometry and a technique similar to the one that we have shown in the previous section, at the end of the previous section, to show that this set of parametric equations actually describes this trajectory, and the equations themselves are not that complicated. So this again, what r here is the radius of the wheel. This is the set of parametric equations that produces the trajectory of this point, or this bubble gum. And the name of this curve is actually, it does have a name, and the name is cycloid. So when you have to analyze some cycloid given to you by this equation, let's, for example, make r equals 2. So let's say you have parametric equation like this, and the question is, what could be the question? The question could be, pick one of the possible trajectories of this of the point described by this equation. So one thing you can do is you can do it by hand. However, I want to remind you that it's totally okay to use technology. So if you ever want to graph this cycloid, given by this equation. So all you have to do is just type this in Desmos. And let's make t equals 10 pi or something, and there you go. So this is what a trajectory of a bubble gum going to look like if the radius of the wheel was 2 units. However, this is not the only interesting curve that we get to see when studying parametric equations. Here's another one. Consider a circle of radius, let's say a, and inside of this circle we're going to have another circle, and let the radius of that circle be b. And here's what's going to happen. You may probably guess what I want to do here, but let's let the inner circle run around the inside of the bigger circle, and let's pick a point and let's observe its trajectory. So again, it's going to look something like this, right? It's going to come here, here, it may come here, it may come here, and again, I don't know if it's going to go repeat here, but it may go here, here, and if the ratio of the radii is nice, then it's totally possible that it will start following its own, like it will start repeating. But if the ratio is not nice, then it's going to create maybe some irrational pattern. But anyway, so the trajectory of this point also has a name. It's called hypocycloid. And the equation, the parametric equations of hypercycloid looks like this. And the y is very similar. And again, if we want to figure out what does the graph of hypocycloid look like, we can use Desmos. So let's take a look here. And I'm just going to type this equation in Desmos. So what I did, I finished typing my x, and I'm gonna copy and paste it here. And we're gonna add this sliders for a and b, and let's make b the smaller radius 1 and a the bigger radius. Let's make it some number, and let's make t some big number. And what we see here is that since the ratio between a and b is not nice, so very unlikely the point will loop in its trajectory, so it's gonna keep moving around and creating these unique paths for each rotation. And well, that's a nice observation. However, when the ratio is nice, so let's say if A is 6 but B is 2, here's what's going to happen. It will eventually loop and start moving over the same path over and over. So again, if the question is asked about hypocycloid, the easiest way to answer it will be to just visualize the trajectory and then look at it and answer the question, such as the number of cusps. In this case, the number is 3. So let's do an example in which the parametric equation is constructed to answer a specific question. Here's a problem. A baseball is hit with an initial velocity of 93 feet per second at an angle of 30 degrees to the horizontal from a height of 3.1 feet off the ground. Use g 32 feet per second squared for the acceleration due to gravity. Determine the height of the baseball after 1.6 seconds. So what's going on when a baseball is hit? How's it going to fly? It's going to fly on a trajectory that is a parabola. And if you recall, the rectilinear motion with acceleration or no acceleration, but constant acceleration or no acceleration can be written like this, right? So I'm going to use letter S. S of t is equal to 1, I guess, S0, the initial position, plus V0 t, V0 is the initial velocity, plus g, well, in general, it's a t squared over 2, where a is the constant acceleration. And we're going to use this formula here to determine the equations for x and y. So let's consider the ball at some time t, and it's going to have the x coordinate and it's going to have the y coordinate. And the initial velocity here is, where is it, 93 feet per second. So what does that mean? 30 degrees to the horizontal. This initial velocity right here will have two components. So we can break down this velocity into the Vx and Vy as vectors. And what would be Vx then? What would be initial velocity? What would be the horizontal component of the initial velocity? Well, this angle is said to be 30 degrees. So we can find the initial component of the velocity using trigonometry. It's just going to be v times cosine of 30 degrees. Or in general, it would be whatever this angle, doesn't matter, right? So that would be the horizontal component of the initial velocity, and the horizontal component of the, vertical component of the initial velocity will be, can be found by taking velocity and multiplying it by the sine of theta. Now, we know that acceleration, the horizontal acceleration, there is no acceleration because there are no forces acting on the ball in horizontal dimension, because here we're going to assume that there is no air resistance. So the horizontal acceleration is 0. However, vertical acceleration is what? Vertical acceleration here is the gravity, right? So if the positive direction is upwards, then the constant vertical acceleration will have a negative sign. So how can we use these facts to construct the parametric equations of this baseball that describe the trajectory of this baseball. We're gonna apply this formula to independently to the motion along the x-axis and to the motion along the y-axis. So along the x-axis, what's going on here? The initial position is x0 plus, let's take the initial velocity, the horizontal component of the initial velocity, and multiply it by t. And since there is no acceleration, then that's it. That's all you need to describe the position or the x-coordinate of the baseball. Now the y-coordinate, on the other hand, will have three components here, right? So we're going to have the y0, the initial velocity, or the vertical component of the initial velocity multiplied by t, and we're going to have minus gt squared over 2. In our case, what do we have? We have the initial position horizontally is 0. The initial velocity is going to be v0 times cosine theta times t, and y of t, what's the initial position? Well, the ball is 3.1 feet off the ground, and what's the initial vertical component, or the vertical component of the initial velocity? It's going to be the v0 times the sine of theta, and so that's different here. T is outside. And times t, and it's going to have the minus gt squared over 2. In our problem, we're plugging in all the quantities. We have x of t is equal to 93 times cosine of 30 degrees times t, and y of t is equal to 3.1 plus 93 times sine of 30 degrees times t minus, and we have g equals 32. So this is the equation. At this point, I am curious, what is it going to look like? I know it's going to be the parabola, but it will be cool if we could confirm that. Let's try. Let's graph this equation. So we have 93 cosine 30 degrees is pi over 6. And we're going to multiply it by t, comma, and then we're going to have 3.1 plus 93 times sine of pi over 6 times t minus 32t squared over 2. And here's what we see. If we allow t to be a little bigger, what do we see? We see the parabola here. And let's answer the question. What did the question ask? The question is asking, what is the height of the baseball after 1.6 seconds? That's rather a simple question. We just have to evaluate y at 1.6. Sorry, so we're gonna compute y at 1.6. So we're going to plug in everything into this equation. I will start evaluating it. The answer is 36.54. So the final answer is 36.5 feet up in the air. The ball will be after 1.6 seconds, and maybe we can see it on the graph here. When t is equal to 1.6, this is where the ball will be flying. So these are just some of the applications of parametric equations. Next we will discuss how to do calculus with parametric equations.